All right, here is objective E1 out of the final unit, uh, letter E. We're going over rational functions and our introduction to it. So a rational function, as you might have heard me mention already, though not in this video, is the quotient between two polynomials. So it's a polynomial in the numerator and a polynomial in the denominator. So a bunch of what we're going to be doing is simplifying those rational functions. We're going to look for common factors between numerator and denominator and hoping to divide them out. A couple of quick things to remember about what we might be doing here. Just going over some basic stuff from fractions. We reduce fractions if we can find a common factor between numerator and denominator. So with 57 over 300, both of those are multiples of 3. So I can divide a 3 out of both. 57 is 3 times 19, while 300 is 3 times 100. So this is 19 over 100. I need to have the same factor in both top and bottom, and those need to be multiplied together. It doesn't count if I'm adding two separate numbers. I need to have a 3 in every term in that case. Also, we're going to be multiplying fractions. That'll be the same as just multiplying across the numerators and across the denominators. Dividing by fractions will be the same thing as multiplying by a reciprocal. So 5/7 over 2/3 is the same as 5/7 times 3/2. 4 over 15 divided by 8 be the same as 4 over 15 times 1 over 8. And then I just carry through like I would with multiplying fractions. Just multiply the numerators and multiply the denominators. 4 times 1 is 4. 15 times 8 is totally a number. I think that's 120. So I could get that. Or I could notice that I have a common factor between numerator and denominator, being that there's a 4 in both the 4 and in the 8, and reduce those to have jumped straight to 1 over 30. 4 over 8 will leave me with 1 over 2. 2 times 15 is 30. Adding and subtracting fractions, we just need a common denominator between the two. So if I'm going to add 2 over 3 plus 4 over 5, I need to get a common denominator on both sides. Looks like that common denominator is going to be 15. So I'm going to multiply 5s into the fraction on the left, while I multiply 3s into the fraction on the right, giving me 10 over 15 plus 12 over 15. And then I can now add the numerators. If I'm adding fractions, one side the denominators are the same, I only add the numerators together. So this is 22 over 15. But let's apply that stuff to rational functions. Again, a rational function has a polynomial for the numerator and a polynomial for the denominator. Here's a few examples. We can either, this first one over here, right there, that guy's got a degree 2 polynomial for the numerator and a degree 3 for the denominator. So that's a rational function. This other guy has a constant, which is a degree 0 polynomial over degree 2. So it counts. And then even polynomials themselves count as rational functions. Since this is a polynomial over 1, but it's 1 counts as a polynomial because it is a degree 0. So polynomials themselves get to count as rational functions, though we're not really going to be studying them too much here because the other parts are going to be more interesting. So given the expression that's right here, x squared minus 4x minus 5 over 4x minus 20, if possible, simplify this expression. Well, I noticed that both top and bottom can factor, so I'm going to do that. My numerator would be x minus 5 times x plus 1, while my denominator, I can pull a 4 out of both the 4x and the 20, leaving with 4 times x minus 5. And now I can start reducing between top and bottom. Any common factors that are in both top and bottom can be removed. Notice that everything is being multiplied together, and I'm going to be canceling out entire factors. So earlier, when things were added and subtracted, there wasn't anything I could cancel yet. I had to first factor everything out before I could start reducing my common factors. It's in this step where I see an x minus 5 being multiplied to both top and bottom that I can remove it. This ultimately ends up being x plus 1 over 4, with one specific caveat here, which be taken into consideration when simplifying this expression. 5 is not allowed to be plugged in for x. So x cannot be equal to 5. Because if I tried to plug it in at the beginning into the original function, I'd have a problem. Even though that x minus 5 reduces out of the expression by the end, I'm still not allowed to plug in 5 because it creates a problem from the get-go. One thing worth noticing in this next example, 3x squared minus 6 over x squared, I'm not actually able to reduce that x squared. I cannot do any cancellation in this thing right here. Because there is not an x squared present in all terms. I cannot factor an x squared out of the numerator, so I can't start canceling it with the denominator. That 6 over there, that minus 6, has no x's in it. So I cannot reduce an x squared between top and bottom. Everything has to be multiplied. So if I look at my next example, uh, this one right here, part A, does have an x in every piece. So I can cancel an x between top and bottom. And it would look something like this. Because that x is factorable, I can pull x's all the way out and then notice that those x's reduce, leaving me with 3x over x squared minus 4. And that's going to be my simplified set. So because an x was present in every single term, I could reduce an x, but only one, because my least power of x is 1. So it's the only one I could get rid of. We also have to add in the extra notion. X is not allowed to be 0 in this function. It also can't be 2 or negative 2. So also, x cannot be 2 or negative 2. But that part's still evident from the reduced form of the function. We had to just take care to remove 0 from our domain because we got to cancel that factor earlier on, because we were able to reduce that factor earlier on. Next up, if I factor this guy, this looks like x minus 7 times x minus 3 divided by x minus 7. And now common factors, I can reduce those. This thing's x minus 3. So it reduces quite nicely, but we still have to add in the extra set, or the extra idea. X cannot be 7 because we weren't allowed to plug it into the original function. Now, 5x over 5x minus 1, this thing doesn't simplify. Nothing to do here. There are no common factors between numerator and denominator, so I just got to leave it as it is. Nothing to see here. All right, so if we're going to start simplifying some of these things, or we're multiplying some functions together, it works very similar to the way that it would with, works quite similar to the way that it would just with regular old fractions. So I might notice right off the bat that I have an x and an x. I also have a 4 and an over 16, so I can reduce all of that to 1 over 4 between those two pieces. Because they're being multiplied together, I am allowed to reduce things across the fractions since they're being multiplied. I can simplify those out. I'll also go through and factor where I can. Specifically, that x squared minus 4 is a difference of squares. So it can be x minus 2 times x plus 2. And I also still have that x plus 2 up there. And now in this step, I again get some pieces that reduce. I have an x plus 2 in top and bottom. So I can simplify that all out, leaving me with 1 over x minus 2 times 4. So that'll be 1 over 4x minus 8. Going again, I've got some more things that can factor. I'm also going to divide by fractions this time, rather than multiplying them. So first thing I'll do is change that division into multiplication. It'll be x minus 4 over x minus 3. So if I highlight all those pieces that changed right there, notice that when I'm dividing by a fraction, it's the same as multiplying by its reciprocal. So I just want to change that to multiplication by the flipped fraction. I'll also factor this thing as much as I can. Looks like we've got x minus 3 and x plus 1 over x minus 4 times x plus 4. And start reducing wherever I can. I have an x minus 4 in top and bottom. I have an x minus 3 in top and bottom. All that's left at the end is x plus 1 and x plus 4. Now, if I want to add two fractions that have, or add two rational functions that have different denominators, I just need to get a least common denominator between the two, or really just any common denominator will do, but the least common is usually the nicest one to work with. So I will take these two pieces and multiply in the part that's missing. So the fraction on the right needs an x minus 1, while the fraction on the left needs an x plus 2. So I'll multiply those two pieces in, giving me a 3x plus 6 over those two pieces together. X plus 2 times x minus 1. Plus, on the right side, this is x squared minus x over x plus 2 times x minus 1. And now that I have the same denominator in top and bottom, I can add these things up. So this looks like x squared plus 2x plus 6. And that isn't going to factor at all. So I'll just leave it as it is. Not a factorable expression. And for fun, I'll multiply the denominator out too. How about x squared plus x minus 2? Another go round. This time I'm going to subtract my two rational expressions, or my two rational functions. So same thing, get a common denominator. On the right, we're missing an x plus 1. And on the left, we're missing an x. I'll multiply those pieces in and see what we get. I've got an x plus 1 over x times x plus 1 minus 6x plus 6 over x times x plus 1. And then subtract these two fractions. Be careful with the negative. It's got to distribute all the way through the piece on the right because I'm subtracting that whole function. So it should look like x minus 6x is negative 5x minus 6. And that'll be over our x squared plus x. Just to add an extra note here, this is going to be x minus 6x plus 6, right? If I put the parentheses around that and subtract it through, that negative needs to apply to the plus 6. Writing some function as a single fraction, well, I have a denominator of 5 minus x, so I'm going to multiply that in to all of the pieces that don't have that denominator. Right? If I want to write this as a single fraction, my denominator needs to be 5 minus x. So I'm going to multiply it in to that other piece. Kind of like this. I want 5x minus 2 times 5 minus x over 5 minus x plus x plus 1 over 5 minus x plus x plus 1 over 5 minus x. And then we'll see what that's equal to. Looks like we'll need to FOIL that out on the left side. So let's do that. Doing so is going to get us a negative 5x squared plus 2x plus 25x, and finally minus 10. Didn't make my fraction bar nearly big enough. Add that back in, over 5 minus x, and I want to add in x plus 1 over 5 minus x. I think whoever made these notes drastically underestimated the amount of space we needed for this example. So I'm going to continue writing below and hopefully fix that in a moment. So this looks like negative 5x squared plus 25 plus 2 plus 1 is plus 28x. And we have a minus 10 plus 1 is minus 9. All over 5 minus x. I think this is a perfectly reasonable place to leave that expression. Though, if you're like me and like having your lead coefficient be positive and also that 5 minus x in the denominator, you'd rather have it x minus 5. We could multiply top and bottom by a negative to get the same result as 5x squared minus 28x plus 9 divided by x minus 5. And this is something we'll see in these rational expressions fairly often, is that if I change every single sign between top and bottom, I have the exact same result. It just, is written to be slightly differently. Oftentimes, if we're solving one of these kinds of equations and we solve on the right side instead of solving on the left side, we'll just get the same answer, except all of the positive and negative signs are switched. So just look forward to that as we go, that if all of our signs are switched, it's the same answer. And that does show up occasionally. So figured I'd introduce it now because I thought it looked nicer that way. Okay, up next, simplifying 1 plus x over y. So step 1 is to rewrite this thing like so. This is 1 over x plus 1 over y times y over x. So notice that the y and the x switched places because I was dividing by a fraction, so that'll be the same as multiplying by its reciprocal. So that's step one, is noticing that that should switch around. Then, we probably also want to get ourselves a common denominator. Let's just simplify this part out first. Because I need to distribute this element to both sides. I'm not able to simply cancel an x because there's no x present in actually, no, I can't cancel the y just because there's a y in that fraction on the right. I can only do that when I multiply it into that piece. So this should look like 1 over, try again, 1 over x squared. And by 1 over, I really mean y over. I just said I can cancel that y. But yeah, y over x squared plus on the other side, I'll get 1 over y times y over x, and that simplifies to 1 over x. So only on the right fraction am I able to reduce that y between top and bottom. Now, get a common denominator between the two. This guy is just missing an x, so I'll multiply it over. And this thing will ultimately look like y plus x over x squared. Right, now, solving rational equations. One of the things that we might do here is clearing fractions. So this idea is going to be multiplying both sides by the least common divisor, meaning that instead of needing to get everything in terms of a fraction with the common denominator, I can just multiply by all of my denominators to have no denominators left over. So what that might look like is the following. I've got 2/3 x plus 3 equals x over 5. And what I'm going to want to do is just start multiplying all my denominators out by just multiplying both sides by my denominators. Now let's take this one step at a time at first before ultimately combining the steps. So what I want to do is I'm going to start by multiplying everything by 3 to get rid of my denominator of 3. If I do that, that 3 again needs to go to every term. So it's going to go to all 3 of these, meaning I'll have 2x plus 9 equal to 3x over 5. Because again, it's got to go to each term. And if I'm multiplying a whole number in, they get multiplied into the numerator. So in the event that I'm unable to simplify things, like with the x over 5 times 3, I'll just call that 3x over 5. It also doesn't matter where I write that 3. I could also have put it out in front to have 3 times x over 5. These two ideas are the same. But I'm just going to keep it up here in the numerator for now. Also notice when I multiplied the 3 into the 2/3 x, I just cleared my denominator over there. 3 over 3 is 1, so 2/3 x times 3. I'm really just looking at the 2/3 times 3 part, but that's just 2. 2 over 3 times 2. 2 over 3 times 3, excuse me, is 2. Then my spot again, multiply by 5 this time to keep getting rid of my denominators. Again, make sure that 5 goes to that 5 goes to every term, leaving me with 10x plus 5 times 9 is 45, and that is equal to 3x. And now I have an equation that I can solve for x. I think I can see that x is going to be negative 45 over 7. I'll get to that in just a second. To prove a point, I suppose, 2 over 3 x plus 3 equals x over 5. I did not need to separate out that least common divisor step into, or my clearing denominator step into two parts. Instead of multiplying first by 3 and then by 5, I could have just multiplied the whole thing by 15, my least common divisor, or my least common denominator. I don't know why I keep saying divisor. But yeah, my least common denominator is 15, so I just multiply 15 into everything. And again, make sure it goes to each of my three parts to come up with the result as follows. Uh, 2/3 times 15. That'll be 30 over 3, which is 10. So 10x. Plus 3 times 15 is 45, equals 15x over 5, which is just 3x. So same result as I got taking it one step at a time. In the future, I'm going to be combining this LCD step into one. This clearing denominator step into just the LCD part, since it speeds up the problems. But anyway, continue solving this thing for x. I'll subtract the 3x over to the left. I'll move the 45 to the right because I want all my x's on one side. And then divide both sides by 7. I get negative 45 over 7. And that does not simplify. So I'll leave this part alone. Coming back up to the question, what makes this thing a linear equation? Well, linear equations, being y equals mx plus b, only have two kinds of terms, an x term and a constant term. So we have a, degree 1 term and a degree 0 term. So if something is a linear equation, I'll only see first degree polynomials on either side. Meaning, yeah, my biggest power of x is 1, and I don't have anything like a square root or an exponential log in there. So it's a linear equation because my highest powers of x is 1. So what do we want to say over here? What makes this thing linear? Only x's, only x to the 1s. Yeah, only x's and constants. Let's try another one. Solving this thing for x. And I want to clear my denominator. It's going to be almost the same. I mean, I think this is going to be exactly the same as cross multiplying. So what I might notice is that if I just cross multiply these two things, I'll get 2 times x minus 1 equal to 3 times x plus 6. That would be our cross multiplication. But really what I'm doing here is just clearing my denominators. My least common denominator here is x plus 6 times x minus 1. And I'm just going to multiply it into both sides. When I multiply it into the left, the x plus 6's reduce. And when I multiply into the right, the x minus 1's reduce. Or again, that's cross multiplying. It's also important to note when we start looking for our solutions, x is not allowed to be negative 6 or 1. So if I get either one of those answers out from this expression, I'm going to have to ignore that solution because it doesn't fit our domain. But if I simplify this mess, I've got 2x minus 2 equals 3x plus 18. And keep solving for x. Maybe you're most excited about putting x's on the left, meaning I'll have negative x equal to positive 20. If I subtract the 3x over and I add a 2 over, which is the same as x equals negative 20. But again, I'll compare that against my restriction, meaning that x can't be negative 6 or 1, but this is negative 20, and that's fine. So we take that solution. And this guy, solving it for x. I need to multiply my least common denominator all the way through. And it might be helpful here to first factor the part on the left. Factor that denominator down there. So x squared minus x minus 6 looks like x minus 3 times x plus 2, and it's equal to 2 plus 1 over x minus 3. So what are we going to do? First, notice that I have an x plus minus 3 that shows up twice. So when I'm clearing my denominators, I only need to multiply by x minus 3 and x plus 2. I also know that x is not allowed to be 3 or negative 2. So if I get either of those solutions, I'll need to ignore them. So let's start solving this thing. I need to multiply this entire thing by that least common, least common denominator. X minus 3 times x plus 2. And that whole chunk needs to go to all three pieces. So this whole bit goes here, and here, and here. Multiplying it all into the left side, the whole denominator reduces, and I just get 5. Multiplying it into that 2, well, I'll have 2 times x squared minus x minus 6. Multiplying it all by 2, I get 2x squared minus 2x minus 12. Maybe I'm going to color code these pieces right here so that we can see they get tied together between top and bottom. Plus the other part, the x minus 3s are going to reduce, so I just have a plus x plus 2 for that final bit. Now I need to gather up everything on one side because I'm going to solve a quadratic equation. So if I do that, I only have one square term, it's 2x squared. I have a couple of x terms. I have a minus 2x and a plus x. So that'll simplify to just minus x. And gathering up all of my constant terms, I have a minus 12 plus 2 minus 5, because I need to bring the 5 over to the right side, getting me minus 15. And generally, when you write 15, the 1 comes before the 5. And the left side's going to be equal to 0. So we should factor that thing. It's going to go to, by using whatever your favorite method is, 2x minus 5. Nope, that's a lie. 2x plus 5 times x minus 3. And that's equal to 0. And I'll solve for my two x values. Either x is equal to negative 5 over 2, or x is equal to 3. Now, check both of these numbers against our original domain. I said that x was not allowed to be 3 or negative 2, which means cannot be 3. This solution on the right is extraneous. So that can't be it. But the one on the right, or the one on the left, excuse me, is fine. Negative 5 halves is not negative 2, nor is it 3. So that solution works. Only one of our two end up working. Okay, and that's the end of E1.